Okay, here we're going to have a look at creating a linear relation from a table of values. Now, if you recall, a linear relation is where a constant change in one quantity produces a constant change in a related quantity. Now, let me give you a table of values that will show that. I've just taken this table of values from a series of diagrams. We were examining the number of plots of land and the number of boards required to build those plots, just to give you some background. Now, if we examine this data, you'll notice that the number of plots were going up by 1 in each case. If we examine the number of boards that are used to build those plots, you'll notice that we're going up by a quantity of 3. Now, the fact that we're going up by a constant amount here indicates that it is a linear relation. Now, what we want to do is we want to build a linear relation from this data. Now, the fact that we have a repeated addition of 3 means that we're going to attempt to build a relation, and this is our this is our dependent variable. Its value depends upon this particular value, which we call the independent variable. Okay, so we want to determine the number of boards that are required based on the number of plots that we have. So the fact, going back here, that we have the repeated addition of 3 means that we're multiplying the number of boards by 3. So as a starter, I can say, well, the number of boards is at least 3 times the number of plots. Now, when we test this out, here, if I have 1 plot and I multiply it by 3, you'll see that that is insufficient to get the number of boards. So we basically do this by trial and error. There are a couple methods, but at this stage we use a trial and error method. So it becomes a case of, now, how can I take the number of plots and arrive at the number of boards? Well, we know it's at least 3 times the number of plots. And by trial and error, if I take this as an example, 3 times 2, well, that's 1 short of 7. So it suggests to me that if I add 1, this might be the relation that links the number of boards to the number of plots. But it's best to try that out fully also. So let's try it out here. Actually, it should be tried out on every value, but I'll just give you an example. So if we take the number of plots as being 3, 3 times 3 is 9, plus 1, 10. So that verifies the fact that the number of boards is 3 times the plot plus 1. Okay, this worked quite well because this was going up by a neat number, going up by a value of 1, and this happened to be going up by 3s. But let's look at another example. I'm just using x and y values. And again, this is my dependent variable, this is my independent variable. In other words, the value of this depends upon that. So I'm going to try and derive the value for y from the given value of x. Now, if I examine the interval widths again, I'm going up by 2, here I'm going up by 2, and similarly here I'm going up by 2. When I examine the intervals with my y values, I'm going up by 6, again by 6, again by 6. So for every 6 I go up here, I'm going up 2 here, which suggests 3 to 1 ratio. So again, it suggests that you could look at it a second way. If I put an intermediate value here, between 1 and 3, 2 as an example, well, the corresponding would be 8. Okay? So, we we really, what we're doing is we're bringing this down. Instead of going up by intervals of 2 here and corresponding 6 here, we're bringing it back down to an interval of 1 to 3, which is the same. So it suggests that I multiply the x value by 3, but when I test it out, 3 times 1 is 3, which is insufficient. It doesn't give me 5. But it does, by trial and error, suggest that if I add 2, I might get the necessary relation. So again, when I go back and try it out, 3 times 1 is 3, plus 2 gives me 5. But you should check that relation out completely. Trying testing it out here, 3 times 3 is 9, plus our 2 gives 11. So it seems to work. 3 times 5, 15, plus 2 is 17. So this is a method you can use to determine the linear relation when you're given tables of values.